Okay, today we will be discussing about equal area criteria applications. So this is coming under the module 6 of your power system analysis, and this is the part 6 of this module. In the last class we already discussed about one of the applications where we are increasing the mechanical input to the generator suddenly. So in a generator we are giving the mechanical energy as the input and electrical power as the output. So when the mechanical power is increased, at that time electrical output is not changed. So what is happening? How the stability is affected? That thing we discussed in the previous lecture. So now we are moving to the second application, which is a fault occurring at the middle of a transmission line. So in this slide you can see in power system, a simple power system network where you can see a generator is here, a transformer, and the transmission lines are connected to infinite bus bar. So this is an infinite bus bar, and the generator voltage is EMF is E, and the terminal voltage or the bus bar voltage or the infinite bus bar voltage is Vs. Now in between that we can see the reactances are represented XT, XL, etc. Now we are giving a mechanical input to the generator. Let it is PS. So PS is the mechanical input to the generator, and it is giving an electrical output PE. This electrical output having three cases. PS is not changed here, it is always constant here, because we are not making any changes in mechanical input. Earlier we have made a change in mechanical input and we analyzed what will be the changes in electrical output. Now here there is no change in mechanical input. It is not changed, but electrical output will be changed with the fault. Whenever there is a fault, there will be a change in electrical output. So let PE1 is the electrical output before the fault. For a healthy system, PE1 is the electrical output and PE2 is the electrical output during the fault, and PE3 is the electrical output after the fault. So before the fault means it is the normal, balanced or the healthy system. During the fault means whenever the fault occurs, at that instant what will be the behavior? What will be the electrical output? That is represented with the PE2, and after the fault means that line is isolated. We can isolate this line. This is the fault and this is the fault, and we can isolate this line, and after that it will be different from the previous system or the healthy system. So these three cases are entirely different. Now what is PE1? PE is normally that representation is EV by X into sine delta. Now PE1 can be represented as EV by X1 equivalent into sine delta 0. Then what will be X1 equivalent? It will be the equivalent reactance of this system before the fault. That is 1. 1 will be representing the before condition. 2 is representing during condition, and 3 is representing after the condition. So X1 equivalent reactance, that is total reactance. It includes reactance of generator XG plus reactance of the transformer XT plus reactance of the line XL divided by 2. Why divided by 2? Because there are two lines which are parallel before the fault for a healthy system. So that is X1 equivalent. So it can be represented as PM1 into sine delta 0. For delta we can say, we already seen that delta 0 is representing the normal or the first condition. Before the fault we can say angle is delta 0. Now what is PE2? It is during the fault. Its reactance will be different. It will not be similar to the reactance before the fault. It will be different. So X2 equivalent is the total reactance during the fault into sine delta 1, and it is represented as PM2 into sine delta 1. Now what is PE3? It is after the fault. X3 equivalent. It is total equivalent reactance after the fault. It is PM3 into sine delta 2. Now, this reactance also we can easily see in Xg, there is no change in reactance for generator, plus Xt plus XL only, because one line is removed. So, it will be XL only. That reactance is increased actually. Okay. Now, you should note down that here PM1, PM2 and PM3 are different. In each case, before fault, during the fault and after the fault, all the maximum power outputs are different. PM is different. PM is different means in each case that power angle curve will be different. Because power angle curve is PE versus delta, we can draw like this. So this is the maximum value for a case, but for another case maximum value is different means it will be having another power angle, and the third case power angle curve is different, maximum value is different means it is having another power angle curve. So in each case power angle curve will be different, but in the previous application power angle curve will be same only. Why? Because maximum power is not changed there. Equivalent reactance is not changed there. Equivalent reactance is not changed with the change in mechanical input. So that point should be noted. Then only we can start the analysis. So the points to be noted here is 1, 2 and 3. That digits are representing. 1 is representing before fault, 2 is representing during fault, 3 is representing after the fault for electrical output and the equivalent reactances. Okay, now delta, in case of delta 0 is representing the previous, the first angle, that starting condition, the angle during the starting condition. So delta 0 is, or the balanced or the normal condition. So delta 0 load angle. Now in each case PM will be different and each cases will be having different power angles. So these points should be noted and we will be moving to the analysis. So this is the curve we are obtaining, that we will see that. So first point is A, that is a balanced operating point, PS equal to PE. We know that that difference can be taken as P equal to PS minus PE. Whatever the mechanical input is given, that much electrical output is taken from the generator. Because it is a normal condition, balanced condition, then these two powers are equal and the difference will be 0. If that condition is satisfied, that means there is no accelerating or decelerating power, there is no acceleration or deceleration, and omega is omega s, synchronous speed, delta does not change at the point A, that is the balanced condition, balanced point. So we can say this is our A, point A, and here angle is delta 0, omega equal to omega s, we are giving a mechanical input PS, and that much PE is produced here. So this is PS and this value is again PE also. Both are at the same point only. So this is a balanced condition. Now we are moving, taking a condition, considering a condition of fault occurring at A. At that point, now at that point fault is occurred. Now what will happen if fault occurs means equivalent reactance increases. So in the first diagram we have seen if a fault occurring there, that equivalent reactance increases and it is changed to X2 equivalent. So if equivalent reactance is increased means then maximum power P max will be decreasing, because PM is EV by X equivalent. In the denominator X equivalent is coming, therefore maximum power is decreasing. That means during the fault, so here we are considering during the fault, maximum power PM2 will be less than PM1. So that curve is having a maximum value of power which is less than the previous case. So we can say it is changing to a point B on another power angle curve having steady state stability limit. That means maximum power less than the previous. And we can see that here in this diagram. So from A, where it is going to B, just another curve it is going at the B. It is having a maximum power less than the previous one. And Now you can see here at this B, what is electrical output? Electrical output be less than this PS. You can clearly see that value of P is less than PS. Here the value of P is less than PS. So what will happen? What will happen if P is less than PS means PE decreases now, no change in PS, and PS minus PE, PS is more and PE is less means it is positive, and an accelerating power is created. So there is an acceleration. When there is an acceleration, omega starts to increase. That is happening from B to C. Due to since P is P less than PS, speed increases, omega will become more than omega S. Whenever omega greater than omega S, delta increases, PE further increases. That you can see in this curve. So here PE less than PS, acceleration happens, omega starts to increase and delta also starts to increase, and PE increases means this curve is representing PE. So in this curve it is moving like this. It is moving like this. It starts to moving like this, and it reaches at C. What is the speciality of that point C? That we can see in the next slide. At fault is cleared at C. So this is the speciality of C. At this point C, we are clearing the fault. So that point C, depending on at which time we are clearing the fault. We can clear it is suddenly, or we can take some time and we can clear. So that point will be depending on how much time we are taking to clear the fault. So fault is cleared and the corresponding line is isolated. So what will happen? X equivalent decreases. It is changed to X3 equivalent and PM increases. So when comparing with the previous case, that just before that, during the fault, X equivalent will be decreasing, and that equivalent reactance becoming X3 equivalent, that we have discussed in the first slide, and PM starts to increase. So PM increases means when comparing with the first case, that is before the fault, X equivalent will be more actually, because in the before the fault we are having Xg plus Xt plus Xl by 2, but here we are having Xg plus Xt plus Xl. So comparing with the before the fault condition, its equivalent reactance will be more, but comparing with the during fault condition, its equivalent reactance will be less. That means comparing with the before the fault condition, its maximum power will be less, but comparing with the during fault condition, its maximum power will be more. So you can it is specified here. So where that curve will come in between those two curves, in between during fault curve and the before fault curve. So it is changing to a point D on another power angle curve having steady state stability limit more than the previous but less than the first. Previous means during the fault condition, first means before the fault condition. So you can see it here. Now the curve is moved, is C to D it is moving, where that curve is coming in between these two, So its maximum value will be, so now at D you can see that electrical output will be more than PS. PS is here, electrical power output is more. So when electrical power output is more than PS means deceleration happens. So at that point deceleration happens, PS less than PE, it is a negative and decelerating power. So it is decelerating power, and D to E, due to deceleration, since PE greater than PS, speed decreases, but still omega greater than omega S. Why? In the previous case, due to acceleration, omega starts to increase from omega S and it increases to some value. So now it is more than omega S. From that point, it starts to decrease. From that, we can say still omega greater than omega S, and omega starts to decrease from omega max. That means at that point omega will be maximum and it starts to decrease. Whenever omega greater than omega S, here again omega still greater than omega S, but it starts to decrease. But whenever omega greater than omega S, delta increases. So PE further increases. You can see here PE further increases here. So it is again increases. So it is moving to this. It is moving to this, and it is coming to somewhere here. It may be any other at any point where this omega is again becoming equal to omega s. It may be here, or any point at any point here, this omega again, because it is a deceleration, omega starts to decrease from omega max, and it is again become equal to omega s at some point, and that point is E. And at a point where this omega is again becoming equal to omega s, at that point is E. So we are having a point E here, then it will be more clear. And you can see at this point our speed again become equal to omega s. Now you can see here still PE is greater than PS. So further deceleration happens, and omega again decreases. So omega again decreases means omega again decreases from omega s, again synchronous speed omega s, and it will become less than omega s. And whenever omega is less than omega s means delta starts to decrease. When delta starts to decrease means what will happen to PE? PE starts to decrease again along this curve. Again PE starts to decrease. Why? Delta is decreasing. Now PE starts to decrease and it is moving like this, and at some point this PE will become less than PS. At that region again acceleration happens. So it is oscillating. From here it is oscillating. Some oscillation happens. In this region, in a deceleration happening. In this region, always acceleration happening. And after this, it will be coming back to a balance or equilibrium point. Not at some other point. So if this point is less than 90 degree. So against that steady state stability, that point coming here. If it is less than 90 degree, the system will be stable. So this point we are obtaining from the equal area criteria. So you can say here in this region it is always acceleration only. So you can say this region can be taken as A1. In this region always deceleration only. You can see it as A2. So comparing this area is measured and compared with these areas are compared. If acceleration area is more, A1 is more than A2, it will be what? Unstable. If A1 is less than A2, it will be stable. And if A1 is equal to A2, that is the critical point to be for the system to be stable. So these analysis we are doing using an equal area criteria. So at E, omega becomes equal to omega s. Fault should be cleared at C such that point E should have a deceleration. If PE equal to PS, critical point for stability. If the point is PE such that PS greater than PE, always unstable. Here at E, consider PE less than PS, having deceleration and omega decreases from omega s. Still deceleration, swing starts at this curve. So oscillation starts at this curve. So now we are moving to another topic, which is critical clearing angle. Critical clearing angle means it is the extreme point where the fault should be cleared. Otherwise, the system will become unstable. So that point is known as a critical clearing angle. So that derivation is given here. We are integrating from delta 0 to delta max. PAD delta, that can be you can see it from in this curve. You can see it here. This is delta 0. From delta 0 to delta max, area should be equal to 0. That is equal area criteria. Two extreme points, delta 0 and delta max. In between these 2 points, that area should be equal to 0. So we are integrating the curve between these 2 points. In between you can see delta C. So up to delta C acceleration, and from delta C to delta max it is deceleration. So delta C is a critical point for stability such that at that point, at least at that point, this should be cleared. So we can say that at that extreme point means critically stable point, or the areas A1 and A2 are equal. So that condition is applying here, and from delta 0 to delta z PAD delta plus delta C to delta max PAD delta, because this is a positive area and this is a negative area, and when adding these two we will be getting 0. So delta 0 to delta C PA means what? PS minus PE2. In delta C to delta max, PS minus PE3 d delta. Now instead of PE2 we are writing PM2 sin delta d delta, and instead of PE3 we are writing PM3 sin delta d delta, and you can just go through this, and if you are having any doubts you can ask me. This is very easy. Actually we are just integrating this and we will be getting an equation like this. This is the equation for critical clearing angle delta C, which is cos inverse of PS into delta max minus delta 0 plus PM3 cos delta max minus PM2 cos delta 0 divided by PM3 minus PM2. You should remember that if we are writing an angle only, it should be in radian, but if we are writing an angle with cos or sine, it should be in degree. Now to find delta 0 at A, that delta 0 is coming, at that condition PS equal to PE1, P equal to PM1 into sin delta 0, and delta 0 can be obtained as delta 0 equal to sine inverse of PS by PM1. Now to find delta max, again at the delta max condition at E, you can see in that picture at E, these two powers are again equal. PS equal to PE3, which is equal to PM3 sin delta max, and delta max will be equal to sine inverse of PS by PM3. But there is some variation is there, because delta max will be always greater than 90 degree, but using this relation we will not get a value which is you will get a value which is always less than 90 degree. So what we are doing an calculation like this, that is we are taking 180 minus sine inverse of mathematically it will not make any changes. So whenever we are taking delta max, we will be taking 180 minus sine inverse of PS by PM3. So by using this relation you can find delta max, delta 0 and delta max. So these are about the how we are finding the critical clearing angle. This is also very important. So this with this we will be completing the theoretical part of the stability analysis. There are some topics are remaining, that point by point method and the RK method. This will be given as assignments. So now with this we are completing the theoretical part of stability analysis. If you have any doubts, you can contact me and you can clarify the doubts. Thank you.